So now we want to find out if these two molecules are identical. And while we know from the first part that they aren't mirror images, we can completely superimpose the two molecules to find out that they're superimposable. And so because they look identical, because they can completely overlap with each other, they would be the same molecule. So we can go now to question 11, which is asking about the same two molecules except when they have the green balls on opposite sides. So I'm just going to take duplicates of all of these. Oops, and it duplicated some extra stuff. So I'm just going to get rid of that real quick. All right. So, and now we just need to change the green to opposite sides. So switch those with the blue ones. Awesome. So now we can check for mirror planes. And so we're going to look at what is and what isn't reflected across this arbitrary mirror plane. So just like the last time, the top white ball and the far red ball are both mirrored perfectly on either side of that mirror plane. But in contrast to number 10, we now have the blue balls completely mirrored and the green balls completely mirrored. So if we're asking about mirror images, we would say, yes, they are mirror images to each other. But what about, are they superimposable? Can we take this molecule on the left, on the right, and completely overlap it with the one on the left? And we'll find that in contrast to the problem above, we can't, because there's no way to rotate this molecule that would fully overlap the red, the green, the blue, and the green without breaking those bonds. So while they are mirror images of each other, they're not superimposable. And since they're not superimposable, they are also not the same molecule. So a little bit different than question number 10. And what's really interesting about these statements in question number 10 is that if two molecules are non-superimposable mirror images, they are also called enantiomers. So that's just a fancy way of saying that statement that we made in question number 11. So question number 12, it's kind of covered, but it's asking how many possible combinations of different molecules with this configuration are there? And we'll find, and you probably found with playing around with your model kit, that you can only come up with 2 different possible combinations, because no matter how we disconnect and reconnect the red, white, green, and blue balls, we're going to get one of these 2 structures with either the green ball on the left or the green ball on the right. And it might take a little bit of playing around with your model kit, which will be super helpful to see that there's only 2 of these configurations. And so we're almost done here. Question 13 is asking sort of a general question about enantiomers. And it's asking on the macro level, which is the larger level, larger than atoms and single molecules, your body has several features that are enantiomers. And remember, enantiomers are non-superimposable mirror images of each other. Name 3 of these features in the human body. And so what's really cool about the body is that you kind of have this like internal mirror plane that's sort of splitting you in half because we have 2 arms, 2 legs, 2 feet, 2 hands, 2 eyes, 2 ears. There's a lot that's reflected on our bodies from the left side to the right side. And so we have a lot of body parts that are mirror images but aren't superimposable. So remember that example from a little bit earlier about our hands. They're mirror images, but we can't overlap them with our palms facing down in a way that overlaps our thumb on the left with our thumb on the right, and etc. So that's an example of an enantiomer for question number 13. So we can have hands here, and then we also want to think about other things that come in pairs that are reflected across our body that we can't perfectly overlap. And so that could be our feet. It could be our arms, our legs, eyes, and I think you kind of get the point. Our ears also works too. Anything that comes in pairs that's perfectly reflected is typically not superimposable. So those would be examples, sort of real life examples of enantiomers. And then question 4 gets a little bit more complex. It introduces this idea of chirality here. And there's a lot of implications of chirality in organic chemistry. So this is something that you'll focus a lot on whenever you take, or if you ever take that class. But there's a few just very simple rules for figuring out if a carbon atom is chiral. And usually when we think of chirality, it's typically with respect to carbon atoms. So that's sort of why we're introducing it here. And so the rules is that the carbon atom has to be, and I'll zoom in on this a little bit, it has to be sp3 hybridized. And that might be a term that you might not be familiar with. All that means is that it has 4 bonds. So that means that we can automatically disregard any carbon atom in this big molecule that has less than 4 bonds. 4, I'll just edit this a little bit, 4 single bonds. So any carbon atom that's double bonded, we can automatically ignore. And all of the carbon atoms in this molecule are represented as these vertices. And this is just sort of a shorthand for organic chemists when they're drawing these enormous molecules. So each of these that I'm highlighting with my little red laser pointer are our carbon atoms. So we're going to cross out all of the carbon atoms that have double bonds. And we're also going to cross out any, we're not going to cross out, but we're not going to consider any non-carbon atoms like the hydrogens, the oxygens, the nitrogens, because chirality is often with respect to carbon atoms. So we're not going to consider those, only carbon atoms. And so we have this first rule. We've already crossed out anything that has double bonds. And then our next is that all 4 single bonds have to be unique. And so that means that we can't have the carbon bonded to the exact same thing twice. And a good example of that is this carbon here and this carbon here. So they're each bonded to some other carbons, but they're also bonded to 2 hydrogens. And these hydrogens are completely indistinguishable from each other. So these cannot be our chiral center. And so that actually leaves us with only one option. And since we don't have any other options for sp3 hybridized carbon, I'm gonna sort of explain this last rule on our correct answer here. So it says that we need 4 unique bonds. And so you might be asking, well, why is this carbon and this carbon unique? Because they're both carbon atoms. Well, the environment around those carbon atoms is actually unique enough that it distinguishes those 2 carbons. This one on the top is bonded to 2 hydrogens, but this one on the bottom is double bonded to an oxygen, which is really, really different than these hydrogen carbon bonds here. And so the other 2 bonds that this carbon atom has is a hydrogen and a nitrogen. And so this fits with our few rules for chirality. And so that makes just this one carbon atom chiral in this particular molecule. So that sort of wraps up our recitation worksheet number 13, but definitely reach out, email me if you have any questions, stop by office hours, and we can go over any of these concepts if you want to hear them again, or maybe hear them explained a little bit differently. So hope that helps.